All right. So the first question that a lot of people were struggling with is this first one. If there's a gas leak in the basement of a building, you'll soon notice an odor throughout the house. However, if there is water leak in the basement, you will need to go down to the basement to detect the leak. Use the kinetic theory to explain the differences. All right, so I've done a very great job at drawing two appliances. This first one is a washing machine, and the second one is a stove. Can't you tell? Okay, so let's say that our washer is malfunctioning and it's overflowing water everywhere, right? Um, so we have a puddle of water on the ground now. Okay, this was like my classroom the other day for those of you that were here. Puddle of water, let's just call this all water, okay? All right, and then coincidentally at the same time, you have a leak, a gas leak from your stove. So maybe you were like boiling some water for some saimin or something, but the flame went out, maybe because of the water, who knows? And now you have gas leaking, okay? And you live upstairs. Oops. You live upstairs in the main house, okay? And this is you. You're hanging out with some arms and some legs, not much of a body. Okay, and you have some stairs that go down. Wow, OMG. Okay, so let's say you're up here and you're like, what's that smell? What's that smell? I smell gas leaking, okay? So you run down the stairs because you smell the gas leaking, right? So why do you smell the gas leaking, first of all? First of all, you smell the gas leaking because gas molecules, remember, gas molecules are flying around in the air with no rules. They're like, screw your rules, liquid and solids. I want to zippity doo dah around. I want to fly around, okay? So they're flying up, they're flying around, and they're moving in random order, and eventually they're gonna make their way, bam, right into your nose. They're gonna hit you in the face, right? And you're gonna be like, what's that smell? I smell propane. What's going on, right? Okay, so you're gonna run down the stairs and address the issue. And you're gonna say, oh, my Simon's not boiling, and I just wasted like an hour's worth of propane or whatever it was. Maybe just a couple minutes, hopefully. Whereas if you were upstairs and you're cruising, you're chilling, you're eating your Simon, you have no idea that your washer is malfunctioning, no noise or anything, right? There's no way you're gonna know if there is a leak in your washer until you actually go down there and you're like, OMG, there's freaking water all over the ground. My clothes are not clean. Oh, what am I gonna do now? Okay, so the reason that you don't know this is because all of those water molecules are in the liquid phase and they are down here, and yeah, they're moving, they're spreading around, right? They're making a big puddle, but they're not like flying around in the air zipping around, right? So we're going to use the kinetic theory to explain this because gas molecules have so much more kinetic energy than liquid molecules do, right? So we'll give them like two little lines of movement here, but they're not moving fast enough to escape to the gas stage. Maybe a couple of these molecules are. What do we call that? When a couple of molecules go from the liquid to the gas stage, but without actual heat energy being applied. What do we call that, you guys? Yeah, we call that evaporation. So you might have some water molecules come up, right, turn into the gas phase, and then they're zipping around. They might run into these other propane molecules that are in the air, but these don't have any smell. You're not actually going to smell water vapor in the air because water doesn't have a smell. All right. So even if they do make their way up the stairs and hit you in your face and your nose, you're not going to actually know that it was from this giant puddle that is forming in your basement now. Okay. So I hope that makes a little bit more sense, but basically what I want you to get from this is we're using this kinetic theory because gas molecules have so much more kinetic energy than liquid molecules do. All right, so you are likely going to be randomly hit by one of these gas molecules and you're going to know something's wrong. And you're going to run down and be like, OMG, what is going on? Today is not my day. Okay, next up, this one was from section 3.2. Explain why water has a different boiling point at the top of Haleakala than it does at sea level in Hana. So there's lots to go into this question, but the main thing that I want you to take from it is that, hey, we're at sea level here in Hana, like we are down here, here's our Hales, right? We're at sea level, and then up at the crater where we're all freezing our butts off, a lot of you said, yeah, it's cold. Well, yes, it's cold. But what we're really concerned about here is atmospheric pressure, okay? So remember, we live on planet Earth, and here is, let's just say, our atmosphere, okay? So when you're down here at sea level, what we call sea level is the same everywhere around the world. It's where the ocean comes up to, right? We have one full atmosphere. We consider one full atmosphere of pressure, right? Because it's not just weightless air that's floating around. No, it's a whole atmosphere. Air has mass, gas still has mass. Okay, so we feel that, right? And when we drive up and change our elevation, do we have more or less atmospheric pressure here? Well, we're going to have less because let's just call this really, really crude. Let's say we're at half an atmosphere now. Let's say we go halfway up to the very to where the atmosphere ends. We make it halfway there. We're on a super, super, super tall mountain, maybe like Mount Everest or something like that. Okay, well, we have, let's say here we're at 1/2 of an ATM is a atmosphere for short. Sorry, I didn't say that earlier. Half an atmosphere. Well, we have less pressure here. So essentially, your pot of boiling water, you're making some, Simon, okay? What boiling point is essentially, and we're not going to go too much into it right now. I don't care that you know this for this particular quiz, but essentially, this water is going to boil when the, let's get a different color here. When the pressure inside of here equals the pressure that is outside in the atmosphere. Okay, so you're bringing up this water energy by applying heat, right? Okay, so you're also increasing the pressure because what are you doing? Well, you're supplying energy, first of all, to those liquid molecules. So they're getting more kinetic energy. They're taking that heat energy and it's transferring into the kinetic energy, which is movement. So they're moving around, zipping around, getting faster, right? Well, essentially, they have to break this liquid barrier by zipping around so fast that they're going to turn into little gas molecules that are going to fly around. All right? So essentially, the whole pressure related to boiling point, I don't really care that you know right now, but I just wanted to give you a little bit more context because when you are up at the top of Haleakala and you got all 3 cabins and you're hiking in the crater for a nice long weekend, which sounds so fun. Oh my gosh, I wish I could do that right now. And you're cooking Simon up there, you're trying to boil some water for coffee or tea or whatever it is that you managed to bring in 20 miles with you. Well, your water is going to boil so much faster because you're at a higher altitude. Okay, you have less pressure that your water has to essentially combat to get from the liquid phase here to the gas phase here. All right. So if I ask you this on the quiz again, I just want you to know about this atmospheric pressure. Not anything too much more about that. All right. Amazing drawing here is for this last question. If you take a balloon from inside a warm house to outside on a snowy day, what will happen to the balloon? Okay, so first of all, here's our house, right? We're warm inside, we're nice and cozy, we got a fireplace, right? It's warm, let's just call it room temperature, everyone's cozy. Here's our balloon. Well, let's say we want to run outside and make some snow angels. So these are my clouds and these are my snowflakes. So Just pretend that there's snow on the ground, okay? Because I don't know how to draw snow, especially with a white background. Here, maybe it's snowing. Okay. And quick review. Oops. Quick review. What do we call it when snow falls to the ground? Or not falls to the ground, but snow, a solid, forms out of a gas, water vapor. What do we call that? What is that phase change called? Answer now. Okay, so we have our balloon and we're going outside into the cold. Well, what's happening here? Okay, so we're inside, our house is warm, and in our balloon we have these gas molecules, all right? We have these gas molecules and they are zipping around, floating around, bouncing off the walls of the balloon, right? Okay, so we're gonna move outside, and what's gonna happen to those gas molecules? Well, essentially the balloon is going to shrink because those gas molecules are cooling down, and what is eventually going to happen if it's cold enough is these gas molecules are going to turn into a liquid. Okay, so you might have, essentially, if it gets super cold, you might have a balloon that is smaller. That's not actually smaller, but you guys, I've lost my touch here. Okay, let's just call it there. Okay, and they are all now on the bottom because they are in a liquid. They've slowed down enough to turn back into a liquid, all right? So essentially all I want you to know is that kinetic energy has to do with heat and energy, okay? So we use these terms interchangeably. Kinetic energy is movement. You can increase kinetic energy by absorbing heat. You can decrease kinetic energy by releasing heat. And that, remember, is called what? What's it called when we release? It means exo, right? Think of it like exoskeleton. Crabs, spiders, and stuff, exoskeletons are on the outside. We are taking this energy and literally in this scenario, taking it outside. Okay, we're releasing energy. We're slowing down. We're moving a lot slower. Okay, losing kinetic energy. And then, oh, last part of this question, could you classify this as a phase change? Well, if we have gas and we are coming outside and our balloon is still full of gas and there's no liquid, then no, there's no phase change, okay? But if we were to develop a liquid inside of a balloon, then yes, it would be a phase change. All right, I hope that makes sense. Let me know if there's any confusion about these concepts still, and I'll try to find another way to teach it.